Hello, welcome to the video. In this section, we'll be looking at 6.1, where we're going to look at exponential growth and exponential decay of functions. So at the bottom here, it says, what are some characteristics of the graph of an exponential function? The first thing we're going to look at is what is the general formula for an exponential function. And the general formula for a function is f of x equals a times it by b raised to the x power. Okay, so this is one of the few times where we're looking at a function that's not a polynomial because our variable is an exponent. So because our variable is an exponent, our graph has some different qualities. So for the first one, we're going to be looking at exponential growth. So anytime we're going to be looking at exponential growth, we are looking at the value of b in our function. If b is larger than 1, we know that it is an exponential growth. If we look at b and it falls between 0 and 1 as a fraction, then we can say that our graph is going to be an exponential decay. So the first part of our um, of our questions is they want you to tell whether the function represents exponential growth or exponential decay. All right, so I'm not as concerned right now about the graphing of it. I'm more concerned about you being able to identify if something is a growth or decay. So again, if we have y equals a times b raised to the x power, so whatever is raised to the x power is going to be our value of b. So since 2 is raised to the x power, 2 is greater than 1, part A is a growth. 1/2 in part B is being raised to the x power. B falls between 0 and 1. It is a decay. Again, these are just being able to tell you whether it's exponential growth or exponential decay. What I would advise you is to try them out yourselves. If you're unsure, please let me know. I'm more than happy to lend some advice. All right, so using um, exponential functions um, in different problems, what we're going to look at is this. It says the value of a car, Y, in thousands of dollars can be approximated by the model Y equals 25 times 0.85 raised to the t power, where t is the number of years since the car was new. They want you to tell whether the model represents exponential growth or exponential decay. So again, if you look at the general form of this, instead of it being x, it's t. So whatever this is being raised uh, to the t power, and it's 0.85. Well, 0.85, it falls in between 0 and 1. So this is an example of a decay. And it makes sense because they're talking about the value of a car as it gets older. More often than not, a car decreases in value as it gets older. Here it's asking you to identify the annual percent increase or decrease in the value of the car. Well, since it's a decay, we know it's going to be a decrease, and we need to find the percentage. So there is two formulas that we are going to look at for our exponential models. The first one, if it was a growth, it would be y equals a times it by the quantity of 1 minus r raised to the t power. Or I'm sorry, this is 1 plus r, I'm sorry. 1 plus r for growth, and then decay is going to be y equals a times it by 1 minus r raised to the t power. Both formulas, a is your initial amount or initial value, we'll call it. R is the rate and t is the time. So looking at this formula here, whoops, looking at this formula here that they gave us, inside here we can say that, well, because it's decreasing, I know that 1 minus r is going to equal 0.85. So basically what we can do is we can solve for r by subtracting 1 and say that, well, 0.85 minus 1 is so I got negative r is equal to negative 0.125. Divide everything by negative 1, r equals 0.15. So 0.15 is my rate, and they're wanting it as a percentage. So my rate is going to be a decrease of 15%. And then the final question here is they asked us to estimate when the value of the car will be um, $8,000. So what you're going to do is you're going to use your graphing calculator. So what you're going to do is this. You're going to go, actually, we'll go up to the original formula and say, well, it is going to be y equals, so it's going to be 25 times it by 0.85, and there's no t, so we'll just say it's to the, whoops, raised to the x power. So that's what it'll look like, and then we'll get our graph like so. So our window isn't so good, so what we got to do is we got to increase our x max. So let's just say it's about 50, and then let's see what that does. All right, so that's a little better. So now we can trace, and now they want you to figure out when, estimated when it's 8,000. So because it's 25, we're basically trying to find where y is 8, because originally this means that it was 25,000. So in order for this to make sense, we have to find y equals 8 in the graph. So finding where y equals 8 in the graph, go a little trace, up, 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 up. All right, so about right around here. So I would say that it would be, and y hits about 7.7, so I would say it's be about 7 years. So about 7 years. Here they give us a problem that says in 2000 the world population was about 6.09 billion. During the next 13 years, the world population increased by about 1.18% each year. They're asking us to write an exponential growth model, giving the population y in billions t years after 2000, and then they want you to estimate the world population in 2005. So what you're going to do is, since they said it was growth, so we're going to use the y equals a times by the quantity of 1 plus r raised to the t power. So because they have it in billions, so it's going to be y equals 6.09 times it by, and this is going to be 1 plus 0.0118, because you have to rewrite this as a decimal, and it's going to be raised to the t power. Well, t after, so it'll be what, 5? Yeah, so it would be 5 because it started after 2000. And when you do all of the math, it comes out to about 6.46. So 6.46 billion will be our answer. In this particular question here, it's asking us to estimate the year when the world population was 7 billion. So, again, we're going to take our graph. We're going to go in here and we're going to type in 6.09 and it's going to be times it by 1.0118 because when you add the two together, that's what you get. And then that's going to be raised to the x power. So get our graph. And so we'll trace it here. And we're trying to find when y is going to be about 7. So it looks like 7, we still got 7.03, which is pretty close, and it's like x is 12.34. So I'm going to say my answer is going to be about 12 years. Here it says the amount y in grams of a radioactive isotope chromium-51 remaining after T days is y equals A times 0.5 T over 28 power, where A is the initial amount in grams. What percentage of chromium-51 decays each day? So we know it's a decay, so we're going to use the decay formula eventually. So what we're going to do is what I'm going to do is I want to break this up and I'm going to say this is y equals A times it by, so it's going to be, I'm going to say this is going to be 0.5 raised to the 1 over 28th power, and then the whole thing's going to be raised to the t power. So I just used one of my properties of exponents to move that variable t, and then I can evaluate 0.5 raised to the 1/28th power and say this is going to be y equals a to the 0.9756, we'll say, and we'll raise that to the t power. So why is that useful? Well, they asked what percent does it decay? So using the formula, I could say that this is going to be y equals a, and it's going to be 1 minus, so 1 minus what's going to give us 0.9756? Well, it'll be about 0 to 0.0244, and that'll get raised to the t power. So right here is our value of r. So our percentage will be about 2.44% decay. Another formula that we'll use in this section is dealing with compound interest. P stands for your principal. It's going to be times by 1 plus the rate divided by n. N is the number of times it gets compounded per year. And then it'll be raised to the n times t power, which t stands for time in years. So looking at a question, it says you deposit $9,000 into an account that pays 1.46% annual interest. Find the balance after 3 years when the interest is compounded quarterly. So how we're going to set this up, it's going to be A equals the principal, which is 9,000, and it's going to be times it by 1 plus, and my percentage is 1.46%, but you have to write that as a decimal, so it's going to be 0.0146 divided by And the value of n is how many times that it's compounded. Well, they said it's compounded quarterly. So since it's compounded quarterly, that means we're going to, n is 4 in this particular instance because there's 4 quarters in a year. And it's going to be raised to how many times it's compounded times it by t years. Well, it's 3, so 4 times 3 is going to be 12. So we have all values here, no variables on the right hand side. So after doing all of the math here, it comes out to about $9,402.21. And that is being able to use exponential growth and decay of functions. I hope this helps. Till next time.